from lunch, everybody. Thanks for joining us for the next session. For this one, we have Vedant, who I'm going to play. So he's still a high school student doing this kind of cool stuff. So as long as I've been doing these events, I don't remember a presentation quite like this. So take it away, and thanks for coming.
Thank you. Hello and good afternoon, everyone. My name is Vedant Mohapatra. I'm a high school senior from Allen High School in Allen, Texas. And today I'll be presenting my research and work on affordable crop disease detection with drone imagery and artificial intelligence. To get started and outline today's presentation, I'll start off with the introduction, the motivation and current solutions available behind this work, my solution and my approach to tackling this problem, including the CNN model used, the drone hardware that was made, the crop disease dataset used to train our model, and then how we trained the model using HPC, and then finishing off with the results and the conclusion we derived from this research. So to introduce, first off, the magnitude of this problem, annually we lose around $220 billion worth of crops due to pests and diseases globally. And this is only becoming expanded in the near future, as by 2050, we'll hit a global population of around 10 billion people, requiring a net 60% increase in food production if we continue to maintain the percentage of crops we lose globally. Now, this is mainly targeted at our most grown and most produced crops, including potato, rice, maize, and wheat, across both the Western and Eastern hemispheres. And now we currently cannot reach these targets, as we are presently tackled with facing our current issue of reaching our crop production ceiling. So right now we're hurt on land, and additionally with this growing population, we're going to be further stressed with more new constraints to our natural resources, such as water, soil and land available, and nutrients available in our land. As with this growing population, we'll need to become more efficient with our land and resource use in the agricultural sector. So then we can further divert these resources to more stressed fields in the future. Now, for the current solutions behind tackling this problem, they tend to fall into two main areas. The first area is lab and soil testing, where this requires manual intervention of a person or a farmer walking the field, collecting soil or leaf samples of crops on their field. Then once they've collected these samples, mailing them to a local lab or university, and then where tests will be conducted on these samples, and then the results will be then returned back to the user or the farmer. This method tends to have pitfalls at having required human intervention, can become costly, as doing these lab inspections weekly or monthly can rack up costs, as well as, especially in the US, most farming is commercial on large fields. So being able to collect data that's representative of your whole field becomes a new issue, especially if you have multiple different crops or plants you're growing on that field. Now, the second method that's a more modern method used today, is using soil sensor arrays, where you'll have a small sensor package that is within the soil, and this is spread out throughout your crop field. And this will be collecting data on the soil, so that way the farmer not only has information on crop diseases, but also can get insights into the pH and nutrients available, giving them insights into the crop health. Now, this can be more advantageous than the previous method, as we now know more in real time about the crop, but tends to price out many smaller family farms, as in America and in the Western Hemisphere, most farms are commercialized, but in the Eastern Hemisphere and specifically Southeast Asia, most farms are between 1 to 2 hectares and run by families, meaning they don't have the manpower or the cost to cover these methods, especially with the climate in these regions during the monsoon season and the rise of tropical storms during the summer. The spread of diseases is even more exacerbated during this time. And these soil sensor arrays are having to be within the elements, and probably will need changing every 3 to 5 years due to their limited battery, and will incur costs periodically due to them having to send the data in real time and then needing a place to store that data. This leaves a gap for a solution that can rapidly and periodically check our fields for pests and diseases that is both scalable and affordable to farmers for early detection at the farm level, preventing the spread of crop diseases throughout our supply chain, and reaching the consumer, which may lead to recalls and diseases or illnesses for human customers. Now for the solution I propose, to use drones to inspect these crop fields to collect video and image data, which can then be fed into a computer vision algorithm to detect these diseases. So with this method, it will arise opportunity for automation across from end to end, where we don't need a human to go in and inspect the fields, but can rather have a drone be autonomously programmed to collect data of photos and images over the fields, which could then be run on our computer vision algorithm to find possible visual marks of diseases present. And this method has been improved in other sectors before, such as with building and infrastructure inspections, and in the electrical sector, where drones are being used to inspect lattice towers and electrical distribution lines to prevent the need for humans to get into dangerous situations and help speed things up, specifically around times when this infrastructure can go down or be affected by the climate. And with drones, this becomes a single package that can be deployed across both small and commercial farms that can be accessible for anyone, minimizes the need for manual inspections, and we can now run tests daily or weekly, providing us more data on where diseases could be present, and also share this with other farmers, so that way we can track the spread of diseases through farms and through our supply chain, specifically with during seasons of hurricanes or tropical storms, where the spread of disease is even more rapidly emphasized. So to start with the foundation of this solution, we start with the convolutional neural network, a form of deep learning to extract features from our images that are collected by the drone. So once the drone passes over a field, it'll collect an image of a leaf or a plant, and then this model will then be run to identify features on this image. Now, in this study, we reviewed diseases that particularly leave physical marks on the plant, such as fungi spots that can vary in color, shape, size, and location on the leaf, which makes it a great feature for this type of machine learning model to extract and be able to identify the disease present in the plant. And then in our case, we created our own CNN vanilla model, which is developed in PyTorch using Python 3, and we conducted this across 10 different crop diseases, across 4 different crops, along with a healthy class as a control group. So we start off from the image collected by the drone, which is then fed through the model either off-site, which can be on-device inferencing, or in the cloud, and then that will then return the disease report to the user. And now on the hardware side of things of the drone, there was a strong emphasis on keeping this affordable and accessible, as that was the main goal of this project. So we started off with a drone, which we ended up constructing for under $500. And this started off with, as a base, a carbon fiber frame with 3D printed TPU components with 4 different 1500 kV brushless motors on a 60 amp ESC. Now, these design considerations were taken to create both a rigid drone with a little bit of inherent flexibility to where it wasn't brittle in case of a crash. And the main bottleneck for drones in this field and why it hasn't been experimented on yet is getting a consistent, stable image with little blur. So these were the hardware considerations taken on a 10-inch drone, to where it'll be resistant to wind at low altitudes and flying at low speeds. So then we can feed in a stable video feed with a high quality image into the computer vision algorithm to get more accurate detections. Next, we included a flight controller and GPS on board of the drone. This was primarily done first off for the automated and autonomous flight that can be programmed. So then with these two systems, the drone will fly autonomously to a pre-programmed path from the user. And then we have live video transmission feed. So that way the user can monitor what the drone is seeing if they're getting a stable video feed in real time. Now in this case, we used a 3,000 milliamp hour battery, which proved to be reliable with a 27-minute total flight time in this use case. But which is great for small farms where we can cover 2 to 3 kilometers of a continuous flight path. But another advantage of using drones in this use case is that it can easily return to a home location, and the battery can be replaced by the user, or it can be used, or larger battery packs can be used, furthering the flight time to be nearly infinite as the drone can autonomously return and then be returned by the user. And we field tested this, although not in real crop fields just yet, but in fields and in windy conditions to capture high quality images with little to no blur in light rain and cloudy conditions, and even with very bright sunlight with little shade. We didn't see too much oversaturation to where those features of fungi on the leaves can still be visible. And an unintended advantage of using drones in this use case was that the prop wash or the thrust wake of the propeller actually blew onto the leaf and helped disperse the leaves of the plant, helping create a more clear image of each individual leaf. And in this use case, we used 5-inch propellers with a very minimal pitch, again to help reduce the effects of wind and create a more stable image at the expense of having a slower moving drone, but we realized that was not a need for this use case. And now for the end-to-end workflow that we wanted to be easy to use by the user. So we start off with planning the mission. So the user can easily create point-to-point flights or waypoint generation flights for the drone, where they can plot points across their field and create and define a home location with geofenced boundaries for the drone to follow, which will be easy to use and have these missions set up to be run periodically, and for the drone to then return and collect this data. Then once the drone is deployed into the field and flies over these fields and collects the image and video data, the data is then extracted from the drone to either be fed for on-device inferencing or into the cloud such as AWS, where we can have our model running and run inferencing on the data that was collected. And then from the CNN model, we'll then return the classified disease detected. And with the GPS on board, we'll have tag each identified disease with a location for the farmer or user to then go into the field and verify that the disease really is present, and stop the spread at the farm level before the crop was even harvested, preventing the spread further down when all the crops are harvested, or further along in the supply chain when multiple farms come together and bring the crops together to be distributed. And now for the data set we used. So as before mentioned, we used 10 different diseases across 4 different crops: corn, rice, potato, and wheat. Some of the crops most affected by crop diseases, as mentioned in the introduction, along with a healthy class for each disease. So we had 14 total classes here, and with the healthy class as a control. And now this data set was publicly sourced from Bangladesh, and this was done for a few reasons. Primarily because this was a region where our system was meant to be applied to, a system or a region greatly affected by the climate and tropical storms, increasing the spread of plant diseases between farms and throughout the region. And also because most of the farms here are smaller and family run, needing a lower cost system that can be run daily or weekly to get that higher resolution, more frequent data and higher frequencies. And as a data set whole, we had 13,000 images with an 80-20 testing and training split that can then be further expanded in the future to include more crops or more diseases or more data to help increase the accuracy of our model. And now for the model training. So our model consisted of 3 main layers. The convolutional layer for the feature extraction of those fungi, as I mentioned, on the leaf, then into a ReLU nonlinearity function, and then a max pooling layer for the dimensionality reduction. And then this was outputted through a flattened layer for the 14 final output classes, one for each disease and healthy class of the crop, using a softmax function. And this connects back to the second part of this study, which was to test the effectiveness of HPC at training these models. So we trained the model on the Ganymede 2 HPC cluster at the University of Texas at Dallas on an AMD EPYC CPU node and on an NVIDIA H100 GPU node. Now to get into the results. So overall, our CPU trained model was run for 15 epochs and proved to have an accuracy of 85%. And then our GPU trained model was ran for 25 epochs because it was trained faster. We could run it for more epochs and had a final accuracy of 89% across the board. Now we had very positive results for our corn, potato, and wheat crops, as these crops had large open leaves with easily identifiable physical altercations from the disease. But we really missed our targets on rice crops, and from analysis, we concluded that this was likely due to the rice crops having a really thin leaf. And now, in an image collected from the drone, we might have plenty of these small leaves with even smaller fungi spots, which make it a hard feature to be extracted, especially with in a photo with lots of sunlight, where a little bit of overexposure or saturation from this extra light can completely wash out the small features we have to go off of, and which is why it was really hurt in the testing, but can be an area of improvement in the future. Now for the comparison between our 2 different nodes. This AMD EPYC CPU node, which was run for 15 epochs, took about 4 hours, whereas our model trained on the NVIDIA H100 GPU node for 25 epochs took about 40 minutes, showing how the GPU node was nearly 500% faster. Now this was mainly done to show the possibility of how training on GPU clusters was the speed of having this fast turnaround time could enable us to quickly tune these models and then spin out what is currently one large model for plenty of different diseases and 4 different crops into their own specialized model, such as having one for a specific region in the Midwest tuned specifically for crop during the winter season, and then having another completely different trained model specifically for potato crops in Bangladesh during the summer season. And having this awareness is only made possible by the rapid training and tuning that we can do on GPU nodes on HPC clusters. And now, in conclusion, we found that we could create an end-to-end crop disease detection system that proved to be low cost at under $500, with the potential to be scaled to any farm globally because of the adaptability that drones give us for this system. And in the future, we first plan on deploying this in the real world, getting testing done on real fields, along with cloud technologies to help test that full infrastructure with having the data collected on site with the drone, and then having the inferencing done off site. This is going to be essential because for a 20, 40, 60-minute flight, recording at 30 to 60 frames per second, we might get 100,000 to 200,000 images from one mission, and we're going to be needing that to be inferenced quickly to get the results out quickly back to the end user. Further, we want to refine our CNN architecture with image augmentation, K-folding, and more layers and more experimentation. specifically to reduce the inaccuracies with the rice crop, and also compare this custom CNN model to popular CNN models like ResNet and MobileNet to get a baseline for how we're performing, and also to see if other avenues are available for us to explore that may prove to be beneficial compared to our current approach. And then, as before mentioned, we want to tackle seasonal awareness, further spinning off our large umbrella one model fits all approach into specific models based on the region, which we believe can return us higher accuracy, and then further increase the scalability of the solution. And back to addressing those smaller rice leaves, we wanted to first off expand the data set we're using, and second of all, tweak our hardware. This may take the form of having not one camera lens, but having two, specifically for the use case. Maybe one wide angle to get as much data as possible, but maybe a second zoom telephoto lens to further zoom in on those fine details present in rice crops. And for the end goal of this project, I see this technology expanding and being most beneficial outside of the visible light spectrum, but rather in near infrared light for multispectral imaging. Now, when crops face diseases or they become ready to harvest, they may give off additional chemicals and pathogens into the air to alert crops around them, or maybe into the soil to alert the crops around them that, oh, we're ready to harvest, or there may be a disease here. You should activate your immune response system. Now, this may not be visible in the visible light spectrum, but switching to near infrared light would be able to point out these artifacts and these features that we can also run our computer vision algorithms on and provide a more detailed image or a more detailed result of what is going on within the crop and what's behind its crop health, providing more than just disease identification, but also how the crop is doing, when is the estimated time of harvest, and more data into and insights into the crop's health and what's going on below the surface, possibly in the soil with the roots and the stem, that could not be visible from just an overhead image. These are the references for any additional images used in this presentation. And this project was accepted to IEEE to be published in January 2026. That is all I have today. Thank you for your time, and I'll be ready to field any questions.
So great talk, very cool project. I'd love to hear the origin story of it, but I have a technical question for you. So you were talking about the range of the drones, and I got the impression that when they were, I don't know if it was they do this automatically or if it's the pilot that brings them back, but when they need their battery changed, do you do like essentially checkpointing, like this is where they stopped, so that they go back to that spot to resume their path? Can you talk a little bit how you do that?
The whole flight is being logged onto the flight controller as like sort of a black box, I would say. So even if the drone crashed, battery disconnected, everything's being logged to that flight controller. So then we can easily reference the, what's it called, the black box, to get the last location, and then it'll resume the mission from that point.
Okay, cool.
Hi, thanks for coming in and presenting your research to the community. So this is a little bit similar to some work we're doing for sagebrush ecosystems in Nevada, where we're missioning drones to go out and do ecological mapping. And I was wondering if you guys have implemented a kind of a two-tier study design, or if you're thinking about this in your future work, where perhaps you do the field flight overview and you characterize like kind of largely what some of the different categories of the crop might be in the field, and then dispatch a second mission that goes in at a lower altitude, higher resolution, and takes very specific pictures in small representative plots to get that finer identification of things like your rice leaves or other features that you see, but you still also need to capture the global for the final analysis.
Yeah, so that was, sorry, I didn't actually think of that before, but that was a good idea. So right now, that part that what you said of having that finer detail pass that I mentioned we wanted to do with the second camera lens. That's sort of done right now. But if we have possibly like a LiDAR scan of the crop field, we would be able to have that data. Then a farmer can decide if we need 2 passes or to split up that mission into 2 paths, which would probably be more beneficial to the user.
Yeah, how we're thinking about it right now is that we do kind of the global mapping at a coarser resolution that may be the final product. And then, now we haven't implemented the real-time mission planning yet, but what we'd like to do is process those data kind of at the edge, whether it's on board or...
Yeah, if I understand what you're
adjacently.
saying, you don't want to run a fine mission across the whole thing, because
No.
that's a waste of time, waste of
Right.
resources.
Yep.
Get that course data done, then we can identify where we want the finer details.
Right, and then either have a second machine, in our case, a second machine with a different sensor, go back and take an oblique view, zoom in, and spatially reference that.
Yeah.
Do the identification in real time, and then, okay, mission is complete, we got this much match, we're good, go to the next
Yeah,
field.
we were also thinking maybe from here it may look like we're doing linear paths, but maybe we can start running the path in reverse, so that way we can get underside of the leaves possibly based on where the wind is heading. And that's another feature, as you mentioned, that we can get.
Cool.
Thank you.
All right, this was a really great presentation. Thank you for giving it. Ag tech is such a huge benefit to the farming community. I think we should be talking more about it. I walked in a few minutes late, so you might have addressed this in the beginning, but did you do any sort of collaboration with any other universities when putting this together, or was this something that you worked on without the collaboration?
So yeah, this was mostly independent, but we did use the HPC clusters and a little bit of guidance from the University of Texas at Dallas.
Okay, is there interest in collaboration? We at in California, UC San Diego, did something very similar with partnership with Sonoma, because there's a lot of agriculture out there, and a few other universities. If there's interest in collaborating, I'll come chat with you after.
Yeah, 100%.
Okay, awesome, thanks.
Yeah, thank you.
Great job. Just want to echo the sentiment. We're really happy to have you here. And joking, it's hard to believe you're a high school student. I see doctoral presentations that are not this good. So, thank you for presenting. The question I have is kind of simple. Thinking about you open your presentation talking about these manual methods of, I guess, clipping leaves and mailing them off to the lab, and then a bit more of a sophisticated approach, of course, of having the in-field sensors. So, where will this land in 5 years? I mean, do you imagine a plug-and-play option for a farmer, who has farmer skills to be able to fly this drone, maybe with or without one of these FAA drone license? I mean, how dumb can we make it such that it can be adopted? Because it's affordable too, and I think that's really a good point.
That was obviously the end goal, because commercial farmers and even small-scale farmers, their goal is, at the end of the day, is to make a profit and keep their costs as low as possible and create as high of a yield as possible. So they won't, if inspecting for crop diseases becomes too much of a hassle, they won't do it. So, and then we'll end up having recalls down the chain at your local Walmart and such. So I think as simple as we can make it is, instead of having possibly a custom drone solution, integrating into off-the-shelf drones from DJI, but currently we have problems with tariffs and selling in the US. But that is a possible avenue. I think right now, if the drone weighs more than 250 grams, which in this case it was around 600 grams, you do need a license, but since the pilot is also using the drone to make money, they do need a commercial license as well. So that's the main handicap. But then after that, you don't need any knowledge, you don't need any experience. It's just an application with the whole end-to-end approach mapped out for you.
Partially a comment, but also a question. Have you considered integrating or reaching out to folks like crop dusters? Because it seems like there'd be some overlap here with the kinds of services that existing crop dusters provide. Human pilots flying a physical plane, providing pesticide, herbicide, whatever. Maybe there'd be some overlap there to help with that problem of getting it out to the
Yeah,
farmers.
that was a consideration when researching drones and why we wanted to use it. As I mentioned, drones are already being used in other infrastructure. And then we also see these huge, like, 1-ton drones that are spraying pesticides and fertilizers across whole fields. So that, as some other questioners have mentioned, that could be another area that I haven't thought of that could be open for collaboration and could further push the needle on this research.
Hey, I had a question. You talked about wanting to use near-infrared scanning in the future to get more details out of some of the crops you're having trouble with. Is that compatible with your current data set of images from, you said that you sourced from Bangladesh, or would you need to start to collect or find somewhere an infrared data set to compare and train those?
Yeah, so that is the main handicap. It's such a new technology and vision system that the data isn't available yet. So that it would be first data collection with the new system, then training and seeing if there are artifacts even present. But promising results have been made from other drone manufacturers of trying to explore this field.
Thank you.
Thank you.
Hi, as everyone said, thanks again for the great presentation. So I have a couple questions. Firstly, could you talk a little bit about what was the motivation behind building your own hardware too, instead of like using something like Trello or the autonomous drones out there, and just putting your own code base on top of it?
Yeah, so mainly was getting the customizability with autonomous flight. We wanted that to sort of be our own process. And the second part was also cost. So this drone was $500. If I wanted to go out there and get like a DJI Air 2S, that would probably run, or a Mavic Pro. I'm now looking at $1 to $5 grand, which is 2 to 10x this.
Right.
So, and also part of the motivation behind it was, so I previously was an intern at a local company where we made software to inspect electrical distribution lines. And that was plug and play into off-the-shelf hardware. And then I saw sort of some of the problems that we had, as I just mentioned, with using that hardware, getting customizability, especially since DJI tends to be closed source. They have their own software that was competing with us that they now offered. So that was sort of the contradiction we were at.
Got it. That's helpful. And in terms of improvements, what are kind of the improvements that you envision on the hardware side? Like, is it putting a better camera on it, or more frequent, images taken, or, a larger battery pack? And also on the software side, what are some improvements that you're thinking of? And do you want to keep it purely like classification problem, or are you also thinking like it would also be able to detect in the future what kind of disease it is, and then maybe, suggest some remedies on top of it? Or is it just going to be like, a disease, yes or no kind of a question?
Yeah, so you actually answered your own question for the most part with all those examples. But first, addressing the final part of that statement, we wanted to identify the specific disease itself that's just done in this study, rather than a yes or a no. Because especially those fungi spots, we don't want those to be mixed up for insects or other particles or dust, especially with regions like the Midwest. That's a pretty big farming region that needs to be addressed. So we wanted to clear up those issues, because otherwise we could get a bunch of false positives that would then create more work for the farmer than the prior methods present. And then the future considerations on the hardware side, everything you mentioned was things that we wanted to explore.
Right.
In addition to possibly more considerations when we get down the road, keeping it lightweight to emphasize that flight time. Because if we start hitting the weight of those enterprise drones, we'll be hit by our battery constraints and our flight time limits, which will then turn users to those enterprise solutions, which will then end up becoming more costly.
Right. Okay, awesome. Thank you so much.
Yeah, thank you.
Thank you so much.
Thank you for having me.